In this theorem, we're going to establish a very important rule for helping us determine whether some series are convergent or divergent, or actually in this case just for showing divergence. So to start out, let's think about the theorem that's being presented here. If the series an is convergent, then the limit as n goes to infinity of an is equal to 0. So what they're saying here is that, okay, if I have an infinite series, of course we know an infinite series is summing up infinitely many terms. So if this series is convergent, the only way that's possible is if the terms of the series eventually get very small. Because if they don't get very small, well then you're going to be adding up infinitely many terms that are not small, in which case, of course, that sum would have to be very large, and in fact it would just be getting bigger and bigger as we add more terms. So here the assumption is that if a series is convergent, then the limit as n goes to infinity of the terms of the series, in other words, each term that I'm looking at in the series, has to eventually get very small. In other words, it has to eventually go to 0. Let's do a formal proof. So we know that if the series is convergent, then we know that the limit as n goes to infinity of its partial sums will converge to some sum, let's call it S. Okay. And then notice that an can be expressed as the difference between the nth partial sum and the n minus 1th partial sum. Okay, so this is because here Sn would be summing up a1 to an, Sn minus 1 would be summing up a1 to an minus 1. And so if I'm subtracting them, all the terms are going to cancel except for an. So all that's left is an. So now taking the limit as n goes to infinity of an, this would be equal to the limit as n goes to infinity of Sn minus Sn minus 1. And this is equal to the limit as n goes to infinity of Sn minus the limit as n goes to infinity of Sn minus 1. These are both just eventually going to converge to S as n goes to infinity. And of course, S minus S is equal to 0. So here we've shown that the limit as n goes to infinity of an must be 0. Now let's see how we can use this fact to help us show something about a series. In other words, what we're showing here is that if the series is convergent, then the limit of the terms must go to 0. But perhaps a more useful way to think of this is if the terms don't go to 0, then the series cannot possibly be convergent. And that's what we're going to call the test for divergence. So if the limit as n goes to infinity of an doesn't exist, or the limit as n goes to infinity of an is anything other than 0, then the series must be divergent. And this is basically just another way of saying the previous theorem. It's using an equivalent way of stating that theorem, just in a different way. This is called the contrapositive of that statement. So this is important. So if I noticed any series where the terms don't go to 0, then right away I could say that that series is divergent. Essentially what it's saying is if I have a series where the terms don't get really small, I'm adding up infinitely many things that don't get small, right? And so an infinite sum means that I'm adding up infinitely many things that aren't close to 0, and so that sum has to be something that approaches infinity. Let's try an example here. Show that the series n squared over 5n squared plus 4 diverges. And this is an example where if I were to just now look at the terms of the series, n squared over 5n squared plus 4, and take the limit as n goes to infinity, what would we get? So in this case, dividing out the n squared from the top and the bottom, I have 1 over 5 plus 4 over n squared. We know 4 over n squared will go to 0 as n goes to infinity. So this limit will equal to 1/5, and in particular, it's not equal to 0. So what we've shown is that if I were to go very far out into the series, the terms are going to be getting closer and closer to 1/5. And so an infinite sum here, I'm adding up infinitely many terms, all of which get closer to 1/5 eventually. Then I'm adding up 1 over 5 infinitely many times. And so that, of course, is not going to sum up to a finite value. That adding up 1 over 5 infinitely many times will have to be an infinite value. So this shows that it diverges. And essentially, we just showed the conditions required by the test for divergence. In this slide, we're going to look at some important properties about sums. So supposing an and bn are convergent series, and then if I multiply some constant by an, then the series there is also convergent. If I sum up the terms an plus bn, then the series that's formed by summing up those two terms is also convergent. And then if I subtract an minus bn, then this series that's formed by subtracting those terms is also convergent. And moreover, we have the rules here that I can factor the constant out from the sum. If I have the sum of an plus bn, I can split the sum over each term. Same with this difference. If I have the series of an minus bn, I can split the sum over the terms of an minus the sum over the terms of bn. Let's try an example that uses those properties. Suppose I want to find the sum of the series 3 over n plus 1 plus 1 over 2 to the n. So starting with the sum property, we know that here we're summing up two terms. So this would equal to the sum of 3 over n times n plus 1 plus the sum of 1 over 2 to the n. Here we have a constant multiple of 3 in the numerator, so I can factor that out from the sum. Okay, each sum going from 1 to infinity. Now each of these sums should look familiar. For instance, here we showed earlier that this was what we call a telescoping sum. Remember when we wrote out the partial sums? Well, first we did the partial fractions, and then we wrote out the partial sums, and we saw that the partial sum formula collapsed down into something that converges to 1. Similarly, this series 1 over 2 to the n, we know this is a geometric series. And we showed earlier that 1 over 2 to the n has a sum of 1 as well. So the sum of the series combining them would be 3 times 1 plus 1, which is 4.